The base of a solid is the region in the first quadrant bound by the x and the y axis. Let's draw an x and y axis. And the graph y equals blah, 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 blah. Okay, for the solid, each cross section perpendicular to the x axis is a rectangle. Okay, hold on. It says perpendicular to the x axis. So I'm going to double check the equation of my line. And yes, the equation that I'm given for my line is a function of x. If the problem says that the cross sections are perpendicular to the x axis, we need a line defined with x. So because x has y is alone and x is all over here on this side, then we know that we're good with this line. So we don't have to change anything. Cool. All right. The cross sections are rectangles whose height is twice its width in the xy plane. What is the volume? Okay, so we're finding the volume of a solid using cross sections based on what I'm reading here. So the first thing we need is an area function. We need an area function for each of the rectangles that are in this region. Okay, that is that we can find in this quadrant. Okay, so we know that the area of a rectangle is width times height. This tells us that the height is twice the width, and the width is what's lying in the plane, in the xy plane. Okay, so our width would be the curve that they give us. That's what's lying in the xy plane. We'll draw a picture later so you guys can see a better picture of it. And then we're multiplying that by twice the height. Now, we should be able to do this without the picture, but I'm going to draw the picture eventually just so that you guys can see it, help you visualize it. But there's our area function. And if we go off of our known formula to find a volume using cross sections, we just need to have the area function and the lower upper bound, and then we're done. We can plug that into the calculator because this is a calculator problem, and we'll find our answer. So we have our area function. Now I am going to simplify this a little bit, but let's go ahead and write out what we got so far. Okay, I put the 2 on the outside because it is a scalar. There he is. And then instead of writing this twice, I write it to the second power. Why? Because I'm lazy, just like all true mathematicians are. Oh, we're not lazy. Yeah, you are. Be quiet. All right, so now what we need is our lower and our upper bound. So now I'm going to draw this really fast to help you guys visualize it. I know right away that my left side is going to be a 0. My right side is probably going to be some x-intercept right here. And let me show you why. Because first of all, I know that the vertical asymptote for this guy is -1 because you can't let the denominator equal -1. And then I also know that there's a horizontal asymptote at -1 because my leading coefficient for the numerator and the denominator both have the same degree, and it's -1 over 1. That's how you find horizontal asymptotes when the degree of the numerator is the same as the degree in the denominator. The degree of the numerator is 1 because there's no exponent on the x. Same with the bottom. And so when they have the same degrees, you take the leading coefficients, the -1 and the 1, you put them over each other. So it'd be -1 divided by 1, which would be -1. Y equals -1. Okay, which means our curve would have to look like this. It would have to intersect the y-axis right here and the x-axis right here. And because we're bound by the x and the y-axes, this is the area that we're looking for. Okay. Well, actually, that's not what we're looking for, but that is the region where our solid is lying. Now, our solid is made up of rectangles whose width is in the region. Okay, so I drew one of them with an arbitrary x so you guys can help, so I can help you guys visualize it. I'm going to come off the page and draw my cross section. Remember, this height is double that of what we have right here. Now, because we're using the x-axis here as our bottom curve, we don't need to subtract anything to find the length of this. We just need the y value of the curve that we're given. All right, so that's going to be our width. Our width is going to be the curve that we are given. Our height is twice the width. Okay, so what is this? intercept right there. That's what we're going to need. And so in order to find that, I'm going to take the curve and set it equal to 0 to find my x-intercept. We don't need the denominator. We multiply both sides by x plus 1 and it goes away. And then I solve for x and I get 3. And so our x-intercept is 3, which means our lower and upper bound is 0 and 3. Next, what we're going to do, because it's a calculator problem, we're going to throw this into Desmos or a graphing calculator. But since we're allowed to use Desmos, why not? That's what it would look like. Now, in Desmos, if you type int, it'll pop up this, or you can press the function button and you can find it. But you put it all in. It's pretty easy because it looks exactly how you would write it. The only thing that Desmos is very picky about is putting parentheses around the integrand. So everything that is being integrated, make sure you have parentheses there. Then don't forget your dx. Then it'll give you your answer. Booyah.